Our goal in this video is to show that if we use both path compression and union by rank heuristics, then the average running time of a single operation is upper bounded by big O of log star of n. Before going into the details of the proof, let's realize a few important facts. First of all, note that since we are now using path compression, it is no longer the case that the rank of node I is equal to the height of the tree rooted at vertex I. However, it is still true that the rank is an upper bound on the corresponding height. Let me illustrate this with a toy example. So assume that we have a tree like this. So this is the root, say vertex 5. Here we have vertex 2. Here we have node 3 and node, say, 6. Assume that currently the rank of this node is 2. This is 0. This is 1, and this is also 0. And now we call find of 6. This will reattach 6 to the current root of this tree. So what we get is the following: 5, 3, 1, and also 6 now stays here, right? So we see that the height of this tree is equal to 1. However, the rank of the root is still equal to 2. Recall that find doesn't use and doesn't change any rank values. Also, for this node 3, its height, the height of the tree rooted at element 3 is equal to 0. However, the rank is equal to 1. Well, intuitively it is clear. Path compression can only decrease the height. So for this reason, rank is no longer equal to the height of the corresponding tree. However, the height is at most the rank. Okay? Another important thing is the following. It is still true that for any root node I of rank k, the corresponding subtree contains at least 2 to the k elements. And this can be seen by realizing that the path compression does not affect any root nodes. I mean, if we have a root node whose height is k, then no matter how many times and for which nodes in this subtree we call find with path compression, all these nodes are still in this subtree, rooted at this node, exactly because this node is still a root. So any node from this subtree cannot be reattached to some other vertex in some other subtree. This node is still a root. So once again, if we have a node who is still a root and whose rank is k, then the corresponding subtree contains at least 2 to the k elements, 2 to the k nodes. On this slide, we discuss a few more important properties. The first one of them says that we have in our forest at most n divided by 2 to the k nodes of rank k. Why is that? Well, recall that if we create a new node of rank k, then it was created by merging 2 nodes of rank k minus 1. Okay? So we know that currently this node is a root. At the same time, we note that the corresponding subtree contains at least 2 to the k nodes. If we have another node of rank k, then it also contains at least 2 to the k nodes. Which means that if we have too many such nodes, I mean too many nodes of rank k, by saying too many I mean that its number is greater than n divided by 2 to the k, then overall we have more than n elements, which is a contradiction, right? The second property is that when we go up, the rank strictly increases. Well, this was clear if we do not use path compression. I mean, if rank is equal to the height of the corresponding subtree, then this is completely clear. Let me recall that if we have, for example, a tree of height 2, then the height of this tree is 2, the height of this subtree is 1, the height of this subtree is 0. And let's say this is element 5, this is 4, this is 8. Now we have path compression, so we need to check what happens when we compress some path. If we call find of 5, for example, then 5 will be reattached to the current root. But it will still be true that the rank of the parent, so let me fix this, this is node 8, that the rank of the parent is strictly greater than the rank of a child. The last property says that when a node becomes an internal node, it will be an internal node forever, right? It will not have a chance to become a root. And this is just because the find operation doesn't change any roots in our forest, while union operation takes two roots and makes one of them a child of the other one. So it takes two roots and leaves only one root. Okay, so once again, when a vertex becomes an internal vertex, a non-root vertex, it will be a non-root vertex forever. We now start to estimate the running time of M operations. First of all, note that the union operation boils down to two calls to find operation and also to some constant time operations. Namely, when we have two roots that were found by two calls to the find operation, we need to hang one of them below the other one, which is a constant time operation. We just need to change one parent value. And also, possibly, we need to change the rank value. Okay? So for this reason, when estimating the total running time, we will just assume that we have M calls to find operation. Further note that each find operation traverses some path from a node to the root of the corresponding tree. So we traverse some number of edges. So the total running time of all the find operations, of all the calls to the find operation, is just the total number of edges traversed. So this is what is written here. We just need to count the number of edges from a parent I, from a node I to its parent J, traversed in all these calls. For technical reasons, we will split this number into three terms. In the first term, we will account all the edges that lead from a vertex, from a node, to the root of the corresponding tree. So the first term includes all the edges that lead from a node to another node, which is the root in this case. The second term includes all the remaining edges where we go from I to J, such that the log star of rank of A is strictly smaller than log star of rank of J. Okay? And the remaining term accounts for everything else, namely for all the edges where we go from I to J, such that J is not the root, and that log star of rank of I is equal to log star of rank of J. We're going to show separately for each of these terms that it is upper bounded by big O of M multiplied by log star of M. Let me show this on a small example, as usual. Assume that we have such a path, that we are going to traverse a path from the node at the bottom to the root of the corresponding tree. So the numbers shown here indicate the ranks of the corresponding nodes. Then these two nodes, these two edges, will be accounted in the first term, just because these two nodes lead from a node to the root of these two edges lead from a node to the root of the corresponding tree. Well, this edge, for example, will be accounted in the last term, because the rank of this node is 17 and the rank of this node is 21, and log star of these numbers are equal. At the same time, here we have 14 the rank 14, and here we have rank 17. And the log star of these two numbers are different. For this reason, this edge will be accounted in the second term. Okay, so on the next sequence of slides, we are going to estimate separately each of these three terms. And for each of them, we are going to show that it is at most big O of m multiplied by log star of n. The first term is easy to estimate. Recall that in this term, we account for all the edges traversed by find operation, where we go from node I to its parent j, such that j is the root. Clearly, for each call to find operation, there are at most two such edges, right? Which means that we have an upper bound big O of m. In the second term, we need to estimate the total number of edges traversed during all m calls to the find operations, such that we go from node I to its parent j, such that j is not the root, and also log star of rank of I is strictly less than log star of rank of j. We're going to prove here that it is upper bounded by big O of m multiplied by log star of n. And this is just because when we go up from some node to the root of the corresponding tree, the rank always increase. However, the rank of the root is at most log n, which means that during one call to find procedure, the log star of rank can only increase log star of n times. Okay? This is just because we have an upper bound for the rank of the root. Okay? It is upper bounded by log n, which means that there are only log star of n different values, different possibilities for log star of rank of all the nodes on this path, which means that it can only increase at most log star of n times. And we have at most m calls to find operations, which gives us an upper bound m multiplied by log star of n. Now it remains to estimate the last term, where we account for all the edges traversed during m calls to the find operations, where we go from node I to node j to its parent j, such that j is not the root, first of all, and then the log star of rank of I is equal to log star of rank of j. What we're going to show is that the total number of such edges is upper bounded by big O of n multiplied by log star of n. Note that this is even better than what we need. What we need is a weaker upper bound, which is m log star of n. Recall that we know that m is greater than n just because m is the total number of operations, while n is the number of calls to make said operations. To estimate the required term, consider a particular node I and assume for concreteness that its rank lies in an interval from k plus 1 to 2 to the k. Recall that this was the form of an interval for which the log star function is the same, is fixed. Okay? Now let's compute the total number of nodes whose rank lies in such an interval. So we know that the total number of nodes whose rank is equal to k plus 1 is at most n divided by 2 to the k plus 1. The total number of nodes whose rank equals to k plus 2 is at most n divided by 2 to k plus 2, and so on. So the total number of nodes whose rank lies in this interval is at most n divided by 2 to the k. Okay? The next observation is that each time when we call find of I, it is adopted by a new parent. And since it is new, so at this point we know that we have a node I and its parent j is not the root. Yes, this is essential. Which means that when we go up, we find another root when we call find of I. And at this point we will reattach node I to this new root. And this new root has strictly larger rank. And this in turn means that after at most 2 to the k calls to find of I, find I will be adopted by a new parent whose rank for sure does not lie in this interval, just because the length of this interval is at most 2 to the k. So if we increase the rank of the parent of I at least 2 to the k times, it will be greater than 2 to the k for sure, right? We now have everything to conclude this proof, to conclude estimating the required term. Recall that we are estimating the total number of edges traversed during m calls to find, where we go from a node I to its parent j, such that log star of rank of A is equal to log star of rank of j. So we've just proved that there are at most n divided by 2 to the k nodes whose rank lies in the interval from k plus 1 to 2 to the k. We then explained why any such node whose rank lies in such an interval contributes at most 2 to the k to the term that we are currently estimating. This means that just all the nodes from whose rank lies in such an interval contributes at most big O of n to this term, right? Now it remains to note that the total number of different intervals is at most log star of n, which means that the total contribution of all such nodes I to the estimated term is at most big O of n multiplied by log star of n. We now conclude the whole lesson. So in this lesson we considered an implementation of the disjoint set data structure where each set is represented by a tree, and for this reason we have a forest of trees. The ID of each set is just the root of the corresponding tree. We've then considered two heuristics. The first one is called union by rank. It says that when merging two trees, it makes sense to attach a shorter one to the root of a taller one. Okay? This helps to keep trees in our forest shallow. And for this, we keep the rank of each subtree rooted at a particular node in a separate array called rank. We then discussed another heuristic, which is called path compression. The idea is the following. When we traverse a path from a node to the root of the corresponding tree, we may want to reattach all the nodes found on this path directly to the root, because this potentially will save us time for further find operations. Right? We then proved that the resulting implementation turns out to be extremely efficient. Namely, the amortized running time of each operation is big O of log star of n. And log star of n is an extremely slowly growing function. In particular, log star of n is at most 5 for all practical values of n.